Good morning and welcome you all to the NPTEL course Advanced Distribution System Analysis and Operation, and we are now concentrating on our module 9, that is distribution network resiliency analysis. In the last class we have seen what is the meaning of resiliency and how we can do the resiliency analysis, and there we have seen a major component, that is the fragility analysis. That means you have to know if any disaster is happening, then how much is your components are fragile. So, today in today's class we will study about the fragility analysis of distribution network circuit elements. So, before that we have to see for distribution systems the resiliency meaning the ability to withstand major disturbances. So, what are those disturbances? Those are mainly natural disasters like earthquake or tsunami or hurricane, cyclone or flood, wildfire, ice storm, etc. Okay. So, you can see few events, the picture of few events, that a tree fallen on the substation, a small pole substation in Gujarat at the time of cyclone, or tree fallen down on the poles lines, and that is in during the Amphan in 2020. Also there is a fallen tree on the distribution line. So, tower collapses due to high compounding weight of the ice and the wind during the snowstorm. So, that also make the towers to bend or collapse completely. Further, you can have floods, that water will be clogged inside your substation, then all the electrical equipments you have to shut down to avoid the short circuit or to avoid the human casualties. So, you can see it, or you can have a wildfire which is very frequent in California. So, if you see that, then everything will be burnt out, your poles, your lines, due to the heating effect. Okay. So, these are the few, you can say, natural hazards already very impactful, already happened in Germany, in California, in Puerto Rico, in US, New York and in Netherlands. So, with these effects, if you have snowstorm, or you can say hurricanes, or you can say wildfire, if this kind of things happen, then it hazardly affect the customers, and more than 1,000,000 customers will become affected by these hazards, and they has to live in dark for few days, and recovery time sometime it becomes more than a month if the natural disaster is a very high natural calamity, if that happens. So, if that is the case, sometime you can see for wind tropical cyclone like Hurricane Mariana in 2017, the overall recovery time has become an year at some areas. So, you can imagine, if your system is not resilient enough, if you have not modeled or strengthened their system properly, then your customers will stay in dark for 1 year time. So, that will seriously question this utility's reliability or utility's trust. Okay. The same events we have seen in India as well, when the cyclone Fani attacked the Odisha, or Amphan for West Bengal, cyclone Yas in Odisha, or Uttarakhand flash flood, or Assam floods. So, if this floods or this high cyclones happens, tropical cyclones happens, so at that time as well the power outage for 3.5 million people during the cyclone Fani. Cyclone Amphan caused over 14 million people affected. Communication and power networks are completely collapsed and 4,000 poles has been toppled. So, these are a huge loss also to the power system utilities, huge economic loss, and that also takes time to recover from weeks to months. Okay. So, depending upon that, you can climate hazards can be summarized, or you can classify them into different categories. First one is the windstorm. If there is any windstorm, the asset affected mostly are the transmission towers, transmission lines, distribution poles and the your substation. What are the common cause? Because of the high wind, vegetation, because the debris that will fall on your pole, soil issues, poor drainage, lack of emergency and multi-hazard stressors. Okay. The typical failure mode is what? Your tower will bend because of the high wind, your equipment damage, your flashover tripping and the corrosion related failures. Okay. Same things you can see for lightning strikes as well. You will get arcing fault, the shield wire or the charge arresters will fail and the circuit will trip. Okay. For high temperature or wildfire things, your line conductor will sag. That means because it is very heat energy it is generating. So, the metal that will elongate, then your sag will loosen and then that will cause your overheating and insulation degradation, soil settlement issues and also the short circuit, and this mainly affect the transmission and distribution lines and the transformers. If there is heavy rainfall, then electrical equipment in the substation will be clogged in the water, you have a water clogging, then outdoor substation and the towers and the poles will be affected and the damage will be due to the floating debris, equipment immersion and tower collapse. Okay? A fragility curve, now you have to define. So, what is that fragility curve? We have to see. A fragility curve is a graphical representation used to show the probability that a system or structure will experience a certain level of damage when exposed to a specific intensity of a hazard. Okay? It will give you that what is the probability to topple down, of toppling down a particular facility when an hazard or a natural disaster happens. Let us say it is a high wind speed or earthquake or water depth, anything. So, that will give you a plot, that will give you a estimation, estimated mathematical estimation of your service failure. So, fragility curve supports stress testing and impact analysis, helping evaluate infrastructure vulnerabilities under extreme events. Okay? And fragility curve represents the probability that a system exceeds a given physical damage level based on a hazard intensity measure. That means, depending upon the intensity and depending upon the damage level, that means one component can have multiple fragility curve. Let us say for a wind speed, we are trying to determine how much it will be mildly affected, then we will see how much it will be moderately affected, then how it is highly affected or extensively affected. So, depending upon the stress, level of the stress or depending upon the imposition or impact of that event on that component, we can say that your fragility curve will be defined or modeled. So, damage levels are categorized by damage states using engineering demand parameters that capture the system response to the hazard loads. Okay? Sometimes damage is expressed via performance indicators like the percentage of the grid affected or the number of users without electricity. That is also a damage. If your customers are living in dark, that is also damage to your system, right. So, the fragility curves can be adjusted to reflect and the anticipated impacts of climate change on power grid vulnerability and resilience. So, how the fragility curve looks like? Generally, the fragility curve function gives the probability of exceeding a damage state as a function of hazard intensity, and it looks like that. In the x axis you will have intensity measure and the y axis you will have probability of exceeding the damage state. That means the probability of failure, and you will plot it. Generally, it is a look like a sigmoidal shape that start near 0, because when the intensity is very low, so probability of toppling down that will be very low obviously. So, that will start from close to the 0 level, but with time or with the increasing value of the intensity measures, that will also increase, the probability of failure will increase. So, that is why the increase of the IM that will approach to the 1, and to maintain this feature, generally it is modeled as a log normal cumulative distribution function with this equation. You can see this is the probability that the damage state, the median value we keep, it gives the intensity at which the system reaches the damage state. That means, lower to that the failure probability is very low and the system will not fail, but above to that the median value the system will fail. So, this will give you the median value, and that you have to define or determine very wisely. Okay. And then sigma is your standard deviation. Now, what is the impact of the climate change on this fragility curve? Whether with the changing climate condition or changing you can say the component condition, whether your fragility curve remains same, or it will be shifted right or left or up or down, something will happen with it, or it will remain same for its entire lifetime, or it can survive any kind of climate change with a single fragility curve. No, your fragility curve will change, and that is the tragedy with the resiliency analysis, that you cannot stick to a single fragility curve, or you cannot stick to a single value. So, what is the design versus increased header intensity? So, let us say you designed a parameter or designed an component for intensity level of IM1. Okay? So, depending upon IM1, you have seen, let us say this is your mean value, median value mu. So, you have designed that for IM1, so you can see the probability level is lesser than that. So, it is fine, my system will can sustain that disturbance. But let us say, and that let us say that is for a mild wind, but because of the high wind or hurricanes, that disaster intensity has increased to IM2. So, by following this fragility curve, now your probability of failure has increased to P2 point, and that is your P2 is greater than P1, and that is at the right hand side of your median value. That means now your component will topple down. Okay? So, this is the impact of the hazard intensity on the fragility curve. Next, effect of damage accumulation and aging. That means your intensity remains same. Now, let us say a pole or a line is 5 years old or 10 years old, then will that sustain that much of intensity? No, that is not the case. So, what is happening? Let us say this is your designed intensity, and this red solid line curve is at the time of installation, what how much is the strength of the fragility of the component, that means the fragility curve at the time of installation. Now, because of the aging or multiple times sustaining your hazards, obviously it will weaken, and because of the weakening, that fragility curve will shift to the left side. Okay. And if it shifts to the left side, then what will happen? For the same intensity level where the probability was low before, now the probability has become higher. So, your P2 is become greater than P1. So, for the same intensity level, if your component age is increasing, or if it is an aged component, or it has sustained multiple hazards, and if you have not done good maintenance of it, then you will experience the topple down. So, the fragility curve is not constant over time, it keeps on moving left or right depending upon your component condition and your hazard intensity. So, how you will determine or develop a fragility curve for a component? First, you will give some input to it, that is the component specification, hazard intensity measures like your wind speed and the water depth, structural model or empirical data, and define damage states. Okay? And the output you will get the fragility curve by doing a probabilistic analysis, because you have told it looks like a cumulative distribution function, looks like a log normal. Okay? So, first step, define the parameters. What are the parameters? Select the component to analyze, that is the pole and the substation, for whom you are trying to derive the fragility curve, which component of your distribution network. Choose appropriate hazard type and intensity, that means choose which kind of hazard you are considering, that means wind speed or earthquake or windstorm, which one you are considering. So, choose that and its intensity measure. Now, define the damage state, that which level of damage you are expecting or you are trying to model from that fragility curve. That means the probability of failure that will show you which level of damage, it is a mild damage or minor damage or significant damage or extensive damage, what you want to see. So, select that defined states and then identifying the engineering parameters. That means, let us say a wind blows, you will see that how much the distribution poles has been tilted, or because of the wildfire how much the stress has been released and your wires has been elongated. So, those things will be your engineering demand parameters, and that you will define. Next, the step 2, you can do the analysis or the data generation in two process. One is model based approach, that for that component, it is an component mechanical component, it is an pole, it is a wear, it is a material strength thing. So, you can just model them in a finite element method and then simulate all that hazard intensity measures, okay, and then plot it. But if you do not have that finite element model, then collect the historical damage data and correlate between your observed damage state and the intensity measure. So, it is a correlation analysis. After that, establish damage thresholds. For each damage state, define the threshold value of the parameter and that indicates your DS exceedance. That means, you have fixed your mu for it. Then generate probabilistic data. After that, for each intensity level, count how many simulations or how many data samples that exceeds that threshold. That means, your mu value. You count it. So, that gives you the probability or the frequency of your failure. Now, choose a probability distribution function, generally a log normal function, and then fit your data, your frequency or the probability data to that probability curve. So, after that you will get your fragility curve, where you will have your intensity measure at the x axis and your failure or the probability of failure at the y axis. Okay? Then plot them and use them in a different application. So, we will see typical fragility curves of the electrical infrastructure. Some examples we will see. First one is that fragility curves for concrete distribution poles versus earthquake. An earthquake is generally measured with peak ground acceleration and spectral acceleration. So, and that is unit of its is in terms of g, that is your gravitational acceleration, okay, in terms of how many times of 9.81. So, you can see that with, if this is your collapse, this is your collapse fragility curve and this is your irreparability fragility curve for different longing distribution poles. This is for 9-meter long, this is for 12-meter long and this is for 15-meter long. Now, if you see the fragility curve with this different length, now let us say this strength of 0.4, let us say, and this red one is your collapse one. So, the intensity or probability of collapsing the concrete poles, if your intensity of your earthquake acceleration is 0.4, if it is 9-meter, then your probability is this much. This probability will significantly increase when you have higher, you have taller poles, if it is a 12-meter, and then it will further increase if it is taller, like it is 15-meter. So, depending upon the height of the distribution poles, though for both the cases your material is concrete, but the fragility curve shifted more and more right. You can see it is shifting right because of the you can say not right, it will be left, sorry, it will be the left direction depending upon the height of the distribution pole. Okay. Now, distribution line versus earthquake. So, if you see the slight damage, moderate damage, extensive damage and total damage, these are your damage states ds, and you have your peak ground acceleration, and if you plot it, the slight damage you will get even for low level of peak ground acceleration, and if it is a very mild earthquake, still you will get a slight damage, but complete damage or total failure needs a high level of earthquake. Okay. So, there are multiple fragility curve for distribution lines versus earthquake. Similarly, wind turbines and earthquake, if you see that your damage states are your horizontal top will be displaced by 1.25% or there is a 5-degree rotation at the tower of the top, 1% horizontal residual deformation, yield stress and complete loss of the tower. So, if you take these 5 damage states and plot them in terms of the earthquake intensity, you can see that loss of tower is only possible when the intensity is very high, but a top displacement is possible when a very mild earthquake attacks your place. Okay. So, depending upon that also your wind turbine fragility curve is changing depending upon your damage state. Now, we see the distribution poles and high wind speed whenever you have hurricanes or cyclone, how it is dependent upon the wind speed. Obviously, if you have an wooden pole, then your probability of failure will be more compared to your steel poles. You can see here the steel and here is the wooden. So, the probability it is very negligible value, but still for wood it will sustain, it will less sustainable compared to your steel when a hurricane attacks. Similar, if your poles are leaned, that means you have not a perfectly vertical poles. Your poles are little bit of leaning, let us say an angle of 30°. This is your completely 90° angle. So, it is leaned, that means this is your 60° and it is leaned by 30°. If that is the case happening, then what will happen? For the then your fragility curve will shift to the left and make your system weaker. So, for the same wind speed you can see the probability of failure for a perfectly horizontal pole is lesser than the leaning tower or leaning pole, and that is almost 18.3% more. Okay. So, that will give you the idea that how you have to design your distribution pole. You have to always see whether your distribution poles are standing in 90° with the ground or not, or perfectly in a horizontal condition or not. Okay. Then you will see the fragility curve for distribution poles for high wind speed with different kinds, that means the age. When you give a new pole, we have seen in the distribution pole, if the class number is less, that means it is a stronger one. So, you see that your, if it is a C3 pole, so all the pole fragility curves are at the right side. If it is a C5 pole, then the fragility curve is at the left side. Okay. Again, if your age is increasing, age of the distribution poles, then the fragility curve for the same pole is shifting to the left. That means, for the same wind speed, previously it is very strong, but becoming brittle day by day with the aging. So, then transmission tower and the line, that is also the same thing. Obviously, the lines are more brittle compared to your transmission tower. So, you can see at the 50, whether 50 meter per second, your transmission tower failure is almost 0.6 or 60% probability. However, the tower falling, line falling is 60% probability, however, the tower falling is 0% probability. Okay. Then your slight damage, moderate damage and complete collapse, this is also the same thing we have discussed earlier as well, that for complete collapse the fragility curve has to be at the extreme right side. Then we will see the distribution line versus the wind speed. Same as the transmission line, the line value, the line will be, the fragility curve for the line is at the left of the tower or the pole. That means, let us say same we take the 60 meter per second wind speed, the line failure is almost 0.7975, that means 75% probability of losing your line, but the transmission or distribution tower failure is lesser than even 10%, right. So, if it is that so, then in that case you can say that your lines are more brittle than your distribution poles. Now, we will see how the length of the line is affected. We have seen that our lines are brittle compared to your pole, that is obvious as well, that is your lines are hanging freely, but your poles are strictly, they are plucked inside the ground. Okay. But if you see a 200 meter line, your fragility curve is at the extreme right. Compared to that, if you increase the length, then your fragility curve shifts to the left side. That means, for a same level, that let us say there is 65 meter per second wind speed, if it is a 200 meter line, long line, then the failure probability is around 20%. close to 20%. But if for the same wind speed, if you have a 500-meter long line, then the probability has increased to almost 55%. That means 35% enhancement in the failure probability. And what that will say? That will say your poles should be very close to each other, and that will give you the mechanical strength against high wind. So, depending upon that, you have to pluck your poles and you have to decide the distance between two poles. Then transmission tower, line and the wind angle. It also depends upon that hurricane is attacking at what angle. If it is completely horizontal with the tower or it is completely vertical with the tower, like 90-degree angle or 0-degree angle. So, you can see if it is a 0-degree angle, that is attacking horizontally, then your strength or the fragility curve is like your system is less fragile. If your hurricane is attacking with a 0-degree angle, then your system can sustain it if in a distribution tower and line. But if it is a 90-degree aligned hurricane attack, then with a simple only 30 meter per second wind speed can entirely topple down your transmission towers. Okay. So, depending upon the angle as well, not only the speed of the hurricane, also the angle of that is equally important for your fragility analysis. This is the overall electrical system compared to your high wind speed, depending upon the category 1, category 2, 3 and category 4, 5 hurricanes. This is the category, different category defined by Saphir and Simpson hurricane wind scale, and you can see the first thing which falls down because of the hurricane, that is your distribution lines. So, that is the first thing. Then the second thing you can say, that is the distribution tower, this one. First is this one, then this one, okay, for lower wind speed, if we go with this one. Okay. So, you can see that compared to your transmission systems or any generating systems, the most brittle or the most vulnerable component in the power network is your distribution system. Okay. So, that is why we are studying this distribution network resiliency analysis. Okay. So, this is for the substation versus earthquake. When your components are anchored, that means plugged with the ground properly, then your complete failure range is at the left side. That means, you see for 0.5 range, this is lesser, but if it is not unanchored, then it is not anchored properly, then your failure probability will enhance. Okay. So, that suggests that whatever substation installation you do, you have to anchor it to avoid earthquake hazard or earthquake disruption. So, distribution wooden poles and wires versus snowstorm. Obviously, if you take the class 2 poles and class 4 and class 5, so with that, with the class 5 poles, this is weaker poles. So, that is less susceptible or that is more susceptible to the wind loading, wind and ice loading, and that will fall down with a lower value of wind or ice. Same for the poles and the wires with the ice thickness. With the wind also, that is becoming brittle very easily, and for ice thickness, for less ice thickness also, if your pole class is more, then it has a higher probability of falling down. So, these things why we are studying these things to see that when your network has this kind of components, class 2 pole, substation unanchored, or let us say your distribution towers, the height, the length between the two distribution towers, length of the line, if these things are not proper, then even at the lower level of the hazards, lower level of the disaster can completely destroy your system. So, that is why we are studying all these fragility curves. Okay. Then this is for the distribution pole versus where and where versus snowstorm. You can see that if the snowstorm angle, also attacking angle, is 0°, same like your failure probability is very less. But if your attacking angle goes to 90°, then your failure probability is very high for both the ice thickness and the wind. Okay. This is for the overall electrical systems that shows the probability failure for a rainfall. So, if you have an intense rain for 3 hours rather than if you have a prolonged rain for 10 hours, which is more dangerous for the distribution network or your electrical systems. Intense rain for shorter time is dangerous compared to your prolonged rain for a longer time. Okay. So, if that happens, then you can see the fragility curve for this intense rain is at the left side. That means, if the accumulated rainfall is 101 and it is happening for the 10 hours time, then your probability of failure is 0. But if it is that so, for an intense, if you got 3 hours, within that 3 hours you got 101 millimeter of rainfall, then the probability of failure is almost 35%. Got it? So, that will say that with the rainfall or the duration of the rainfall, how only the not the duration, but also the accumulated rainfall, how your system will respond, how much system will you will lose because of the rainfall hazards. This is the water logging, that is obviously there. Even a simple logging of water or very less depth of the water, your system failure is very high. Why? Because you have a water clogging or logging at the substation, that means your equipment has been immersed in the water. So, you cannot afford to switch them on, you always have to switch them off to avoid any kind of a short circuit or human casualty. Okay. So, that is why a very less depth, even in 1 meter depth, if you go to 2 meter depth, then you would reach to the 100% failure for high voltage, medium voltage and low voltage, all kind of electrical substations. Okay. Then distribution poles versus tsunami. If you have tsunami hazards, obviously those are your systems will become very vulnerable against that for different kinds of utility poles, concrete, your steel. But still, if you can see, if your steel poles height is less than 5 meter and if you do it at the greater than 5 meter, you can see for the greater than 5 meter, this fragility curve has been shifted to the left compared to the lesser than 5 meter. So, to make where your system is more prone to the tsunami, like there is more prone of happening the tsunami. So, at that time your the utility pole's height must be very short, that it will not get the direct hit from the wave, just to avoid the direct hit. Then the water will flow above it, it will rescue himself from that itself from the direct hit of the waves. Okay. So, with this is the fragility analysis. With this I will end today's lecture, and we have learned how we can design the fragility curve and how the fragility curves are varying with the different natural conditions. And even for different electrical components it is different, and for different natural conditions also it is varying. It is not a constant quantity. Okay. So, whenever we will do the resiliency analysis or we will check the strengthening of a power system or distribution network, we have to consider accordingly that which fragility curve suits us best. Okay. Thank you.